You'll now learn how to solve regression problems. Regression problems are where we predict a number, a value, using other data. For example, this could be continuous values like temperature, which can range from 20.3, 20.4, etc., or marks, which may be integers like 0, 1, 2, 3, all the way up to 100. You learn how you can build a model without writing code, how you can change the model parameters by adding more data or changing the model itself, and how these get exposed as APIs, that is, web pages where you can pass parameters as input without writing any code. Let's tackle a regression problem now. In this data set, we have data for different dates starting from the 8th of August 2013 daily all the way up to the 6th of November 2013. That's for a period of almost 1 quarter. For each of these dates, we have the following information. The value of the Australian dollar against the US dollar, the Brazilian real against the US dollar, the Canadian dollar against the US dollar, and so on. For example, this 0.897 represents that the Australian dollar is worth 0.897 US dollars. The Brazilian real is worth 0.4347 US dollars. And all of these are on the 8th of August. And the values change as the dates progress, fluctuating up or down. Given this information for all of these currencies, and in some cases we have the information for commodities as well. XAG is silver, XAU is gold, and XBT is platinum. So given this information, can we predict whether the price of a particular currency can be identified using the information that we have in the rest of the columns? For example, is it possible to predict what the Australian dollar will be based on the Brazilian real itself, or perhaps even based on the date itself? Let's now create a new container that is going to predict the values of currencies. We'll call this project regression. That's created the project. We're going to click on edit to launch the IDE. And now we'll create a microservice using ML handler. This microservice, let's put it at the endpoint /predict. At that URL, we'll upload the currency data set. This currency data set should have the following columns: date, Australian dollar, Brazilian real, and so on. Effectively, the values of each of these at different dates. Now, what we want to do is predict the Australian dollar using the Brazilian real. Let's see how well that works out. We'll choose the outcome column as AUD and the columns to exclude as all the columns except for Brazilian real. So we'll remove BRL, and now all the columns except AUD, of course, and BRL are excluded. We can decide whether these two columns are categorical or numerical. They are numerical, but that is the default. So we'll leave it at that. It auto detects and will put them as numerical columns. Next, we choose a model. We need to choose from a regression model because the problem that we are now tackling is one of regression, that is predicting a number rather than picking a category. Let's use the first regression model. We will tune this model later and click on submit. Now that has added the ML handler at the location /predict, which means that when I click on preview URL, it will allow me to train the model and give me an API that exposes the results. The regression prediction endpoint now has data where we can predict the Australian dollar from all of the columns except for the one selected, which is basically using the Brazilian real using linear regression. Now we can choose a metric to figure out how accurate this model is. One measure is R square, which roughly says how much of the variation in the Australian dollar can the Brazilian real explain. Another is maximum error, which simply put is based on this prediction, what is the largest error. Mean absolute error is what is the average of the absolute error that we get. Mean squared error is what is the average of the squared error. And root mean squared is what is the average of the squared error in a square root units. It doesn't matter which of these measures you pick because by and large you'll be picking one measure and consistently choosing from across the models. But there are a couple of things that you need to keep in mind. R square is a reasonably good measure. Max error is useful only when you want to make sure that the highest error is low and you aren't too worried about whether the others are close or far away. A slightly better measure is mean absolute error or mean squared error, where you look at whether overall the predictions are good. Mean absolute error is good if you want the predictions to be as close to the base as possible. Mean squared error is good if you want the predictions, the lower value predictions or the lower deviations to be ignored a little more, and the higher deviation predictions to be suppressed further. Root mean squared and mean squared error are practically the same thing. The only difference is in the units. The root mean squared is the square root of the mean squared error, and the units are similar to the values we are looking at. We're going to be looking at R square as a measure for this particular set of exercises. Let's see which of these models has the highest accuracy as measured by R square. We'll start with linear regression and then move on to each of the other models. So for linear regression, when we train it, the R square we get is 83%, which is not bad, but not great. Passive aggressive regressor, when trained, gives us a negative R square, which is clearly not good. SVR gives us a slightly negative R square, still not good. New SVR gives us an 88% R square. Now that is better than the 83% we saw for linear regression. Linear SVR gives us slightly worse at 0.82. So new SVR is still the best we have so far. And K-neighbors regressor has a 92% R square. That is the best model we have so far. Decision tree regressor comes at 99%. That's hard to beat, and that is certainly the best so far. And random forest regressor comes close behind at 98%. And MLP regressor gives us a minus 25, clearly nowhere near as good as we'd like. So of the models that we have, decision tree regressor seems to be the closest. Let's see if it's really close. Now let's pick a value out here. Let's say 0.4402. At a BRL value of 0.4402, the Australian dollar was a 0.9204. So let's see how close it gets to that. 0.4402 predict. That gives us 0.9204, which is exactly the value that we see here. So that's good. What about at 0.4388? It should get 0.9204. So 4388 predict. And that gives us a 0.9204 as well. What about 0.439? That gives us a 0.91975, which is slightly off from the 0.9149, but still pretty good. So this as a model is giving us fairly good results in contrast with, let's say, something like linear regression, which is giving us only a 0.83. Using just linear regression and only the value of Brazilian real to predict the Australian dollar, we only get an accuracy of 83% with linear regression. Let's see if data alone can improve this information. Supposing we added Canadian dollar, that is, we no longer exclude Canadian dollar from predicting the Australian dollar. So using the BRL and CAD values, what's the accuracy of AUD? That takes it from 83 to still 83, no improvement. So adding the Canadian dollar made no impact. What if we added the Swiss franc as well and retrained? That takes it up to 85% R square, slightly better. What if we added the Chinese yuan and retrained it? That takes it up to 93%. That's much better. What if we added the euro and the British pound and trained it? That takes it up even higher to 95%. Perhaps if we added all of these, with the exception of date, and made a prediction, it would take it even higher. Sorry, I should have done it as deselect all with the exception of date and then trained based on this. And yes, that takes it to as high as 99% with the same model. So you see an alternate way of improving a model's accuracy. We can add data, and alternatively, we could change models. One risk with adding data is that if you have relatively few rows, we only have 91 rows worth of data and lots of columns, then it can easily overfit. For example, if you had 91 rows and 91 columns, you will always get 100% because it's always possible to fit these 99 columns in some way to get to the exact right result. So it's generally good to make predictions based on relatively few columns compared to the number of rows, and instead pick different models to try and iterate and get to something that works best. Let's take a quick look at how the API works behind the scenes. I'm pressing F12 on the browser to get to the console, and in the network tab, when I click on predict, I see a new request. Let's click on this request. And in the payload section, it says that it's sending the following payload: BRL 0.4347, Canadian dollar 0.9612, effectively all of the parameters that we've entered here. And this is being sent as a request to the URL /predict. When this request is being sent, you can just see this by opening it in a new tab. The response that we get is all of the same information that we provided, plus an additional row that says that the Australian dollar has a value of 0.89878 and so on for this input combination. This is what gets displayed when we make a prediction. While the input payload does not have the Australian dollar, it ends with XPT, the response does have the Australian dollar added. And this allows us to create an API that allows anyone to pass any set of parameters. Like for example, like let me change the BRL value to 0.48. And when I press enter, let's see how the Australian dollar changes. So that's changed a little bit from what used to be 0.8987 now to 0.8973. If the value of the Brazilian real increases to 0.50, then it predicts that the Australian dollar will dip to 0.8966. This API can be used to create front-end applications.